Here's an introduction into vectors and some products of vectors that we're going to be using as kind of our toolkit to build the more complicated calculations and algorithms on top of for the remainder of the course. Starting with the coordinate system, which is basically our world, or the frame that we're going to be working in with all of our calculations. We see here a two-dimensional coordinate system, which is fairly simple and we've all used before in trigonometry and other courses. Basically an xy coordinate system with x extending to the right, y up. And then we have two three-dimensional coordinate systems. One of them called the left-hand system, the other one called the right-hand system, and the difference lies basically in which direction we decide to extend the z-axis or add the z-axis to this already established xy system. So a coordinate system, a three-dimensional coordinate system, basically has these four things: a point of origin, and in this base coordinate system the point of origin is simply 0, 0, 0, and then it has three axes, and we can represent them as the unit vectors I, j, and k. I being 1, 0, 0, j 0, 1, 0, and k 0, 0, 1. And in some cases we'll use these vectors as part of specific annotations, specifically when we're dealing with cross products and other things. But I, j, and k are simply the unit vectors parallel to the axis of the coordinate system. So in this coordinate system or coordinate frame, we can represent specific types of geometrical objects, mainly points and vectors. The difference between a point and a vector being that the point has a position in space or in the coordinate system, but no specific orientation or direction or size, just a position. And the vector doesn't have a position, it only has a size and a direction, or an orientation, or length and angle. However we look at it, it has orientation and size, but no position, whereas the point only has position. And here we're looking at basically a vector as the difference between 2 points. Thereas imagining that the vector would be the length that you need to travel from the position P to the position Q. So adding V to P gives you Q. On the other side, where we're viewing a point as a translation of another point by the vector. So adding V to P will translate P into Q, and at the same time subtracting P from Q will give us the vector V, representing the distance between them, or the direction and length needed to travel between them. So to begin with, we'll give two vectors here in 3 dimensions, which we're going to use for a few definitions here, or calculations that we can do with vectors. To begin with, we can take a vector and we can add another vector to it. This is something that is easily possible, and the only thing that's done is you simply take the x coordinates and add them together, y coordinates and z coordinates, and graphically you can see on the right side that it looks basically like the vector that would begin where you start drawing A and end where you end drawing B, if you draw them in a line, basically starting B where A ends. Multiplying a vector with a scalar is allowed too, but here the scalar will be multiplied with each coordinate of the 3-dimensional vector, or n-dimensional vector, respectively. So the resulting vector will have the same direction, the same orientation as the original vector, but the size is the only thing that will have changed. So it will be longer if the scalar is bigger than 1, but if the scalar is between 0 and 1, or between -1 and 1, we'll have a shorter vector, but the direction will be the same. unless the scalar is a negative number, then the direction will be exactly opposite, but it'll still be in the same line, parallel with the original vector. So in every case, the resulting vector will be parallel with the original vector. The negative vector is simply the original vector multiplied by -1. We can set it forth as a specific definition here. A minus A, they both have the same length, they're parallel, but they have the opposite direction. Subtracting vectors is, we can also just view that as adding the negative vector to a vector, but graphically here on the right side you can see that if you basically draw A and B in a way where you start them at the same place and draw them from there, then you can take each of their ends and the difference between the vectors will be a vector between those points. So those are all fairly simple and straightforward operations on a vector. But going into something a little bit more complicated and a little bit more interesting, we see the dot product of two vectors is basically defined as such. If you take the dot product of A and B, you'll multiply each coordinates respectively. You'll multiply the x coordinate of both of them together, you'll multiply the y coordinates together, multiply the z coordinates together, and then take a sum of all of this, and you end up with a single number. It doesn't matter how many numbers or how many dimensions each vector is in. They have to be of the same amount of dimensions. But in either case, you're always going to end up with a result that's a single number. So this is a way to quantify the relationship between vectors in a specific way, which we can use in a lot of different calculations and operations. And the dot product has some properties. For starters, it doesn't matter in which order we take the dot product. It's symmetrical, the dot product. We can also use the dot product more or less like multiplication when we're doing algebra. So if we take a sum of two vectors and take the dot product of that sum and the third vector, we could just as well have taken the dot product of each of the vectors with that same vector b and taking the sum of the resulting numbers afterwards. Same with multiplication with a scalar. It doesn't matter whether you multiply one of the vectors with the scalar before you take the dot product, or if you take the dot product first and multiply with the scalar afterwards. So this is useful when doing algebra with the dot product, but probably the most interesting property of the dot product has to do with the length. So the length of the vector squared equals the dot product of the vector with itself. It's the same thing to say that the length of the vector is the square root of the dot product of the vector with itself. So here we have a way to calculate the length of vectors. Obviously, if this is in 2 dimensions, this is simply the regular trigonometry rule that we know about the length of vectors. Simply the square root of x squared plus y squared. But this is a bit more general in this case for any number of dimensions. So to use the dot product now in something of a relevant setting, we're going to look at the problem or the example of finding the angle between two vectors. This is actually something that we use in computer graphics for calculating light, calculating the effect of light on a specific surface, because in that case we want to know what the angle is between the normal vector to the surface and the vector pointing from the surface to the light. And the closer to parallel these are, the stronger the intensity of the light, or the effect of the light on that surface. So this is very relevant, and all we need is just a clever way of using the dot product and a clever way of setting up the coordinates for the vectors. So what we start by doing is simply saying, rather than representing a vector as just its coordinates, we're instead going to say we're going to represent the vector as its angle from the x-axis and its length. So we're going to take its length multiplied with the cosine and sine of its angle from the x-axis. It doesn't really matter which spot exactly we take. The x-axis, however, looks the most like the unit circle that we're used to dealing with when we're working with angles in trigonometry. So this would be the best point to start. And in the end, what we're trying to find is the angle between two vectors, meaning that we want to find the angle that is the difference of the angle of one vector to the x-axis and the angle of the other vector to the x-axis. So to find a correlation here between the dot product and the angle between vectors, we're going to look at these two vectors. So the vector b is the length of b multiplied by the cosine and sine of the angle theta b, which is basically the angle from the x-axis up to b. And the same for the vector c. If we simply take the dot product of these two vectors, b dot c, we can see that we end up with their lengths multiplied, and this multiplied by the cosine of theta b times the cosine of theta c plus the sine of theta b times the sine of theta c. And so we're going to look at a classic trigonometry rule that tells us that if we have the cosine of two angles multiplied added to the sine of two angles multiplied, that'll always give us the same number as taking the cosine of the difference between the angles. And there suddenly we have the difference between these angles. That is the difference between the angle from b to the x-axis and the angle from c to the x-axis, which is the angle we were looking for, because that is the angle between the two vectors. So now suddenly we have b dot c equals the lengths of b and c multiplied times the cosine of the angle we were looking for, or we can also say the cosine of the angle we were looking for equals the dot product of the vectors divided by their lengths, or the dot product of each vector's unit vector. So if we take each vector and make a unit vector with the same direction, we can then take the dot product of those vectors, and that'll give us the cosine of the angle. So having the cosine of the angle will very simply reveal to us the angle itself. So we can now say that we basically have two ways to describe the dot product itself, either by the cosine of the angle between them, between the vectors multiplied by their lengths, or the regular definition of the dot product. So this actually reveals to us one more interesting property of the dot product, which is that if a dot b equals 0, the angle between the vectors is exactly 90 degrees. So the vectors are perpendicular to each other if the dot product equals 0, and we don't even have to calculate their lengths. So this is a way to give us sort of a correlation between the vectors, approximation for their angle, without having to spend calculating power on actually calculating their length. At the same time, we can say if the dot product is a positive number, the angle between them will be less than 90 degrees. If it's a negative number, it'll be more than 90 degrees. And if it's exactly 0, they'll be perpendicular to each other. And this we use in the lighting calculations as well, because exactly 90 degrees, then we don't really have to take the lengths. We can just use that perpendicularity. But what's more important is that if the angle between them is less than 0, if the angle between a normal vector to a plane or normal vector to a surface and a vector from the surface to the light is more than 90 degrees, then we're actually not interested in calculating that light, because that light will be shining on the back of the object, on the back of the surface, and it won't light it at all. So in the cases where a light is actually lighting up the backside of a surface, we can simply skip part of our calculations, skip rather expensive parts of the calculations that we're doing. But if it actually is larger than 0, the dot product, then we'll go on, actually calculate the lengths, divide them if we need to. In some cases we're working with unit vectors anyway and we won't need to. But either way, we can optimize our calculations a little bit by using this property. Okay, one more product of vectors that we'll be using specifically in 3 dimensions is the cross product. And in linear algebra, this is a very much used product. I'm not going to read the whole thing aloud, it's there on the slide. But in the end, the cross product is of 2 3-dimensional vectors, is the third 3-dimensional vectors, and has these coordinates. So the x coordinates, the y coordinates, and the z coordinates are calculated, as you can see here. And, well, here are some properties. The unit vectors I, j, and k can be calculated as such from each other. And this is just a simple way to imagine in which direction the resulting vector will be. It's not symmetrical, so A cross B is not the same thing as B cross A. It's in fact the negative. In the same way that I cross J would not be is K, but J cross I is minus K. But in the same way as the dot product, it doesn't matter if you take the sum of 2 vectors first and then do a cross product with the third vector, or if you do a cross product with each of them and then sum that up. And a scalar can be multiplied into either with the resulting vector of a cross product or with one of the vectors before you take the cross product. However, probably the most interesting property of the cross product is this. A cross product, if you take the dot product of a cross product and either of its own vectors or either of the original vectors, you get 0, meaning that a cross product of 2 vectors is perpendicular with both of the other vectors. So this can easily be used to calculate a normal to a plane, a normal to a surface, and is again very important when we're doing lighting calculations. That is, we have a surface, we now have 2 products that give us a possibility to calculate lighting, or calculate the effect of lighting on a surface. That is, one of them can yield us the normal itself. The other one, given the normal and a direction to a light, can give us the angle between those vectors and thus the intensity of the effect the light has on this surface. So for lighting calculations, both of these products, the dot product and the cross product, are very important. So that's basically the end of this short introduction into just these couple of products and properties of vectors that we're going to be using from now on. And next lecture will be on matrices, matrix multiplications, and transformations using matrices.